Okay. Good morning to everyone and good afternoon to the other people from outside of South America. Hello everyone, and thank you for joining us in this new webinar season that is part of the International PhD School of Advanced Oxidation Processes. My name is Daira Escudero Perez, and today I'm moderate of this seminar, which is going to be presented by Professor Juan Matos Lale, who is going to talk about his work entitled Carbon-Based Material for Photocatalytic Application. Okay, so before starting with the webinar, I would like to introduce a few aspects about the International PhD School on AOPS. It's important to remark that International School was founded in 2014 as an initiative of academic and scientific with a strong and international recognizing expertise in the environmental application of AOPS. The main aim of this international PhD school was promote the higher education of young scientists in this research field. All this initiative is mainly coordinated by Professor Luigi Riso from the University of Salerno in Italy, but we have other coordination for Europe that is coordinated from Professor Sixto Malato from Plataforma Solar of Almería in Spain. And for the case of Latin America, the coordinator is the Professor Ricardo Torres Palma from the University of Antioquia, Colombia. Currently, the school has 73 scientific committee members of 53 institutions from 24 different countries that include 119 PhD students. It is important to highlight that the school has different initiatives and support to PhD students, like organization of a specific training events such as summer school or webinars, to promoting networking to create new opportunities for school members, and keeping PhD students updated about new positions, conference, and other relevant news. It's important to highlight again that if you have other information requests for a possible affiliation, can be please contact to Professor Luigi Riso, that is the email, for other kind of information. Now, to continue to this presentation, now I'm going to talk about the academic story of Professor Matos, who completed his PhD in surface physics and chemistry through the Franco-Venezuelan Postgraduate Cooperation Program between the Central School of Lyon in France and the Venezuelan Institute for Scientific Research in 1999, studying the influence of carbon materials in heterogeneous photocatalytic reaction and solar nanotechnology. In particular, he is a co-founder and director of the Chilean Association of Carbon Material and co-founder of the Latin American Carbon Federation, of which he was its president from 2016 to 2018. Professor Matos was the director from 2017 to 2021, together with Professor Conchi Ania, co-director, of the Franco-Chilean network of evaluation of biochar for application in energy and environmental remediation. From 2015 to 2019, he was professor of the postgraduate energy of the Faculty of Chemical Science at the University of Concepcion and researcher of the Technological Development Unit at the same university. In 2020, he moved to the Institute of Applied Chemical Science of the Faculty of Engineering of the Autonomous University of Chile, where he is currently a permanent full professor and the director of the PhD program in Applied Science. Regarding research, Professor Matos is founding director of the Smart Nanomaterial Groups, whose aim is to efficiently design of different types of nanomaterials, such as semiconductors, hybrids, different types of carbon-based material, such as carbon activates, biochar, among others, and systems doped with heteroatoms for the application in the conversion, production, and ecological storage of different types of clean energy, such as hydrogen production, solar cells, cell of fuels, photocatalytic environmental remediation processes, mainly pollute water and air, as well as the production of solar fuels. It's important to say that he has made some 288 conference presentations that include 92 plenaries, keynote, and guest lectures. Moreover, he has a total of 213 publications, of which 90 articles have been published in high-impact journals and several books, about 3,000 citations, and an age factor of 27. Additionally, he has developed different international research projects and collaborative technological applications with Mexico, Spain, and France. And he has been director of projects with Chilean funds, such as Fondef IDEA, Fondesit, among others. Finally, in the year 2021, he has received the recognition of the international scientific community for being catalogued in the 2% ranking of the most influential scientists in the world. Please, Professor Matos, the floor is yours.
Daira, for this presentation. I am very happy too, of course, to be here, and welcome to you all. It's a great pleasure to give you a big part of our job in carbon-based materials, specifically for photocatalytic applications in hydrogen photoproduction and in solar treatment of water. Of course, it's a great pleasure to be part of the International PhD School on Advanced Oxidation Processes. We have here very, very good friends and colleagues from more than 20 years ago. So, go ahead. So, I will try to convince you that there is a kind of correlations between the pore confining effects and the surface molecular density of the molecules absorbed on nanoporous carbons. And nanoporous carbons that plays the role themselves as a photocatalyst. And I will focus only in two important and very modern applications: hydrogen photoproduction and, of course, solar treatment of water. And we are talking that they are still modern applications, but they have been discovered more than 40, 50 years ago. As you well know, titanium dioxide has been reported as the best one photocatalyst all around the world in any kind of photodegradation of pollutants or even biological pathogens or microorganisms. And the mechanism of work of the photocatalysis involve the excitation of electrons from the valence band to the conduction band. And that plays the role of promote reactions in the surface of the semiconductors to create or to form two very interesting types of reactive oxygen species, like superoxide anion radical or hydroxy radical. They play the role of catalyst in reductive reaction or in oxidation reactions. However, in spite of that, titanium dioxide have a great, enormous advantage as a highest photoefficiency, resistant to strong acid bases. It's very photostable on the UV radiation, is relatively bioinert and cheap, or that is supposed that. However, it has a very important limitations, operative limitations. First one is the high recombination rate of the photocouple generated. It's very sensitive to the pH of solution that can lead to the deactivation of the hydroxy radical forms under irradiation. The third one is very limited to work only with a very sharp region of the spectra of the solar spectra, since it absorbs only around 6 to 8% of solar spectrum. At the same time, most of the titanium dioxide from commercial origin has very low surface area, so they are doomed to work with very limited to diluted system. But in addition, a couple of years ago, it has been discovered a very interesting kind of result that led to the French Ecological Authority to list titanium dioxide as a suspected carcinogen. And it's very interesting, but since 2 years ago already, France have been forbidden the use of this titanium dioxide in food or cleanup compounds, for example, shampoos and soaps and so on. But we suspected these several groups 30 years ago, and we have started to work with a combination of materials. And we started a line that we talk about carbon-supported photocatalysts. And we have dealt with different kinds of carbon-based materials, but also with silicas or combinations of nanoporous carbons with silica. But by far, carbon material is the best support used in photocatalysis. More or less 94% of all the papers concerning with supports in photocatalysis deals with carbon materials. And in the last 2 decades, it can be seen an enormous increase in the use of nanoporous activated carbons, nanotubes, and graphenes. And this is amazingly, but even higher than 1 million of papers about carbon and catalysis and photocatalysis, around 87% have been published in the only last 2 decades. That is the importance of the carbon materials. And the reason is because they have what I talked 25 or 50 years ago, multifunctionality of carbon materials. We can control the geometrical forms in the kind of monolith. It's a kind of cake, it's a kind of cake of carbon. We can control the pore size distribution. We can control the topology of the porous in the shade of pillared mesoporous carbon. We can control the exfoliation, the intercalation. We can control even the possibilities to promote the formation of what we mean like graphene like foams, as in the bottom and right part of the slide. You can see here also that the reason of the high reactivity of carbons, not only in thermal catalytic promoted reaction, but also intrinsically as photocatalysts, is due to several factors: topology, pore size distribution, high surface area, and in addition, it is relatively easy to control the functionality. We can include different kinds of interesting groups, as for example, nitrogen doped, potassium intercalation, phosphorus intercalation, oxygen intercalation, and at the same time, we can control the formation of carbons, and carbons are very reactive and very useful species for photocatalysis. In the specific case of Chile, where I'm living now since 7 years ago, we have potential opportunities for the development of solar energy and water remediation by using advanced oxidation processes. You can see in this map that Chile has the highest photon flows all around the world. We are talking about around 2,800 kilowatts hour per meter square. But the first example I'm gonna try to show you is exactly about the hydrogen production. Why hydrogen? There's many reasons of why hydrogen is very important today as an energetic vector. But 2 of the most important physicochemical properties are that hydrogen has the highest energy content per unit weight in comparison of any kinds of energetic dispositive. At the same time, hydrogen has the lowest energy density than any other system. So it's very useful for high energy production, and at the same time, it's very useful for the locomotive purposes since the very low density it has. That's the reason why with only around 300 million tons of hydrogen, we are able to produce 1 terawatt of energy. So now we are dealing in what it is talking about the century of the hydrogen. In other words, we are dealing with more and more production of hydrogen in the following years. Examples: 2015, 1 terawatts of hydrogen has been produced all around the world. In a couple of years ago, 2.4 terawatts. It is already achieved 12% of the global matrix energetic all around the world. And in 3 years in the future, in 2025, we will achieve around 23% of the global matrix. That means around 5 terawatts of energy. But what kind of hydrogen we are talking about? We are dealing now with around 80, 75, 80% of what we are talking gray hydrogen, and more or less around of 10% of blue hydrogen, and still only very few quantities of the so-called green hydrogen. Okay, green hydrogen, it could be the future, but there is still an important quantities of operative situation and environmental situation that have been to be solved before the maturity of the green hydrogen technology. For instance, green hydrogen technology only use very clean energies to be storage in batteries to alimentate an electrolyzer. That is the place where the catalysis will deal. And we need water from sea. And it is amazing, but I told you that we require around 300 millions of tons to produce 1 terawatt of energy. It means that in the comparison of 18 to 2 grams per mole, we require around a factor of 9. It means that for each terawatt of energy we want to produce from hydrogen, we require 2,400 millions of tons of seawater. That is a huge quantity. So we could have a very important problem in the coast of the sea, of the zones close to the sea, because of the extraction of seawater. So there's no easy to talk about green hydrogen. In paper, it's fantastic and it's a reality, but still we are dealing with gray and blue hydrogen. Green hydrogen is those hydrogen that can be achieved from the reforming of hydrocarbons. And the only difference is that in blue hydrogen, we can achieve very high purity hydrogen, call it blue hydrogen, from methane. Methane is around 85–90% of all natural gas composition. But the difference between blue and gray is the capacity to sequestrate the carbon dioxide or carbon monoxide in units of sequestration of carbon dioxide. So that is the only difference. But even today, we are dealing around with 8% of all the hydrogen around the world is produced from the reforming of hydrocarbons. And it means with gray hydrogen, and around 10% of blue hydrogen, maybe 1 or 2% of green hydrogen. The other difference, what we are talking here in this presentation, is yellow hydrogen. Yellow hydrogen is the strictly spoken hydrogen produced by photocatalytic processes. No photovoltaic, no winds, no batteries. Directly, instead of using an electrolyzer, we require more efficient photoreactors to produce yellow hydrogen. So, in this matter, carbon materials plays an important role because we are able to control different kinds of topology, from graphene, from fullerene to graphene, passing through multi-wallet carbon nanotubes. My group has around 16 years of experience producing hydrogen by different ways. We have producing reforming by steam, reforming by partial oxidation, hydrogen from dry reforming or with carbon dioxide reforming, and even by controlled cracking of methane from natural gas. This is the gas conversion scheme, and depending on the type of catalyst, you are able to go by different by different routes. And depending of the stoichiometric relations between the hydrogen and carbon monoxide, you are able to produce the methyl ether. That is a very important additive in gasolines, methanol, or even paraffins. We are able to arrive even to produce carbon-12 by this way, by Fischer-Tropsch synthesis. We have published different kinds of situation around carbon-based materials in hydrogen production. We have explored the different possibilities with catalytic promoters. We have optimizing the operative parameters using nickel-based catalysis. We have explored noble metals as platinum or ruthenium. We have dealing with very acid catalysts as niobate perovskite types catalysts, and even we explore mesoporous pillaret carbons by using lanthanides and Sirius catalysis. But in a more recent work, we have dealing with that we are talking about as corrugated graphene or crystalline nanosized graphene. And we are able to produce graphene in a very high surface area, even as 2,200 meters square per gram, with a very high micropure volume by using a biomass waste as rice husk, for example. We have published this one 4 years ago. And it's very useful, this kind of nanostructured carbon materials, because we are able to control the topology in a very well-ordered graphene that when we reconstruct the topology, we are able to see that all the graphene layers are very, very well established with rings of 6 carbon atoms. But when we are in presence of corrugated or this very high distorted graphene, we are able to introduce defects. The defects are very important in photocatalysts because they introduce change in the electronic density of the graphene layers. And the reconstruction of graphene corrugated materials, we have in presence of networks of materials with pentagons, hectagons, and so on. So with this kind of material, we are already obtaining very, very interesting result in hydrogen production and changing the nature, the chemical nature of the product by using alkaline earth materials or zinc oxide or copper oxide. We are able to control the deactivation. In absence of promoters, the activation of catalysis achieved even until 60% in only 4 hours. At the same time, we have been able to control the surface functional groups and to control the pore size distribution of nanoporous carbon materials to induce the formation of very high ordered and very equal diameter of carbon nanotube. For instance, we can see here this example, and you can see the increase of the quantity of carbon deposits in the shape of multi-walled carbon nanotube. You can see here this point that I noticed with the laser point, and this is what we are talking about, a baby carbon nanotube. We are in presence of carbon windows, and the carbon windows permits the use of nanoporous carbon as a template to produce a high quantity of carbon nanotube. And it is a very important result because it's the first demonstration, the first experimental demonstration of the forming of windows in the layers of the graphene materials, as was reported by Vallejo Burgos and Kaneko 4 years ago. So, but what's going on with the hydrogen photoproduction? This is not a new reaction. So I like when people talk about the green hydrogen, but I always, with very respect, I try to say that this is not a new reaction. It has been published 50 years ago by Fukushima and Honda. The reason of lead in the forbidden this reaction is because the efficiency of titanium dioxide is very pure on the solar irradiation conditions. So, but it can be notably increased by using different kinds of sacrificial agents at the same time by using coadditives to the catalyst. No? So this reaction has been increasing in the last 10, 15 years. And for example, we have published 10 years ago with Hermenegildo Garcia from the Institute of Technology, Chemical Technology in Valencia in Spain. We have reported, for example, the difference between water as an electron donor in comparison of ethylenediamine tetracetate. When we employ this molecule as an electron donor, we are able to increase by a factor of 45 the hydrogen production with a very single photoreactor, very single. When you don't have too much money to start a laboratory, we need to be creative. In a very single reactor and with a Hamamatsu fiber optic, we are able to produce hydrogen in a very high quantities. At the same time, we achieved our correlation between the confining pore effect estimated by the ratio between the micropore volume against the total pore of volume of the carbon and the quantum efficiency. The highest is the quantity of nanoporous, the more important is the pore confining effect within the pores of the support, in this case, nanoporous carbon. And you can see that is a great relationship between the ratio that is able to measure the pore confining effect and the quantum and the relative quantum efficiency. And we propose a modification of the classical mechanism of the hydrogen photoproduction in terms of the electron affinity of gold that it was our catalyst. But I forget to say, just only you can see here that in absence of gold, titanium was practically negligible the photoproduction of hydrogen. So we require a species active in the visible range of the solar spectrum of irradiation. So we are living in Chile. So the next step was to less the gold and work with copper because the electron affinity of copper is around 140 kilojoules per mole. So in this result, we go back to very old results that we published more than 10 years ago to the production of carbon quantum dots. And when we deal with that, we were able to control the not only the mesoporous, but also we were able to control the empty inner spaces of the spherical forms of carbon quantum dot and copper doped titanium-based hybrid photocatalyst. This microtonomy was published 12 years ago for the case only in presence of titanium dioxide. We were able to control the inner space of the sphere that introduced an increase in the harvesting light efficiency. In other words, if you have a mesoporous ordered material able to get through the lights or irradiation through the solids to the inner space, once it arrives to the inner space, there is no scattering. All the light is confined within the sphere. That is why we are talking about of a harvesting efficiency factor. And we published it 12 years ago. And more recently, 3 years ago, we demonstrate the possibility to reduce the energy band gap to around 2.8 electron volts for titanium dioxide based photocatalyst with only 1% of doping of carbon. And the carbon in this supercell was able to control the possibility to be excitated under solar irradiation. With that in mind, we construct a new kind of material, but instead of carbon alone, we are doping at the same time with carbon and copper. And with carbon and copper, we were able to produce this kind of very ordered materials for the case of titanium dioxide and very high distorted species for copper doped materials. But the important here is in presence of only 4% of copper, we were able to increase the hydrogen production by a factor of 9. So that it means with the confining pore effect. In other words, if copper is able to be protected by an important layer of carbon material, it does not suffer lixiviation or oxidation. So that's a very interesting result that we are early to be published in the following weeks or months because it depends on the time we can get free in the following weeks. So concerning to the solar treatment of polluted water, once we have been able to optimize some parameters by using a solar simulator, we are able to scale up to almost industrial size prototypes of photoreactors in the shape of CPC photoreactors. This one has been constructed by my group in Chile, and the change we have introduced in this kind of dispositive has been able to achieve a Scheilen patent. So what's going on? We have a long history using porous carbon materials in photocatalysts, more than 20 years ago working with this. We are able to control to the topology from very close topology, even close to molecular sieve with between the layers in the order of 0.5 nanometers, very close to graphite 0.33 nanometers. So we are able to produce very close topology carbons, or even more open topologies, and introducing functional groups. And depending on this kind of situation, we are able to achieve different mathematical models that deals with the production of hydroxy radicals, and we are dealing with the topological control. Graphene plays the role of semiconductor, more or less in the shape of graphite. And here, the higher is the pore confining effect measured by the ratio between the microporous volume against the total volume of pores. The higher is the photoactivity and the synergy between the carbons and titanium dioxide. And it means with the order of the topology. At the same time, if the control is not dealing by the topology, but the surface functionalities, we produce, more importantly, quantities of superoxo anions radicals. And this is why, because we are in presence of quinones or carboxylic acid in the surface of carbon. And those functional groups are very easy to be excited from pi to pi and from pi to anti-pi orbitals by visible light. Are very easy to excite that, and we are dealing with the phenomena of the photoassistance of the catalyst. In this case, it doesn't matter. You have very high surface area carbon. It does not depend on that. It depends on the surface control. And depending on the quantity of this kind of functional group, you achieve a maximum of photoactivity, and immediately you start to decrease. So, with that in mind, we were able to construct the different kinds of mechanisms in terms of the topology or basic surface of the carbon, and that permits to control the selectivity to the para product, starting for chlorophenol, for example. And here is more important the production of hydroxy radical, and therefore the reaction goes very fast to the degradation of the pollutant. On the other side, if the control is by the surface, we are dealing with the photoassistant to promote the formation of superoxo anions radical that are able to inject hot electrons to the conduction bands of the titanium dioxide to promote the formation of more quantities of superoxo anion radicals. In this case, reaction does not go by the unimolecular substitution, unimolecular nucleophilic substitution, but also by electrophilic addition, because hydroxy superoxo radical also play the role, a bipolar role, of very strong reductive species or a very soft oxidation species. In this kind, if it plays the role of electrophilic addition, we are able to control the ortho product, and at the same time, a very green, eco-friendly methodology to produce hydrogen peroxide. We have achieved a prize years ago because this mechanism in any congress, I really forgot it. So, more importantly, is in a very recent words, we are dealing with the free metal and free semiconductor photocatalysis concept. And this is because we are able to demonstrate that carbons not only are coordinated by means of the functional groups in the sulfates to the to titanium atoms in the vortices of the octaedra of titanium dioxide. But we proposed that the formation of a non-stoichiometric titanium oxide in the shape of titanium 3, oxygen 5, because the coordination, it was unable to reduce titanium 4 to titanium 3. So it means that the real photoactive species is not titanium 3, is not titanium 4, is titanium between 3 and 4. At the same time, we reported the possibility to form in situ superoxide anion radicals in very close topology nanoporous carbon. And more recently, we demonstrate the possibility to form hydroxy radicals in carbons in absence of semiconductor. Of course, the quantity, the intensity of the hydroxy radical is more or less the half of the titanium dioxide, but it means that we do not require semiconductors to promote reactions of photodegradation, okay? So we are able to work with free metal and free semiconductor photocatalysts only, but very well controlled properties of the nanoporous carbon. So it is possible to scaling up this methodology. We think yes, we are able, because now we know which are the active sites, are most importantly, not only superoxide ion, but also hydroxy radical that are formed in the surface of the carbon. We have already demonstrated that can be regenerated. We demonstrated in a paper 2 years ago. And more importantly, we know now that the active sites are not only in the surface, they are intercalated in the pores. It means that the higher the pore confining effect and the possibility to form oxygen or nitrogen or sulfur basis species within the pores, we are able to induce very high reactivities in carbon materials. The problem is how to explain correctly the reaction rate. It's not possible to explain now with the classical Thom or TOF definition. We cannot explain correctly the quantum yield of the carbon-based porous material. The reason is because the Thom or the turnover number is defined by the moles converted of reagent against the quantity of catalyst, all right? Is the number of mole of substrate converted by mole of catalyst. Alternatively, you can talk about moles of a specific product forming in steady state conditions against the moles of catalyst. At the same time, turnover frequency is defined by the Thom against the time in the point that the product achieved the steady state condition. So this is a kind of I give you one and to give me two, and it's very tough to me to say the joke in English. Sorry, pardon me. But the important thing here is for most relevant industrial application, a TOF in the range of 10 to minus 2 to 10 to 2 is required. If you are not able to achieve these values, your technology is unable to be scaled out in real industrial application. At the same time, the quantum yield is defined by the number of mole of substrate converted by mole of photons absorbed. But in the case of carbon materials and dealing with solar irradiation, you can achieve, or you can think about the high quantity of photons we have in a real solar CPC photoreactor. So this quantity is so high that it doesn't matter that you have a very high converted fraction of reagent. The quantum yield is very pure, and it's not the real reality. It's not the reality of the reaction rate you are following up in your system. So we require another way to explain the photocatalytic reactions of porous materials in absence of metal and in absence of semiconductors, okay? And we need to take into consideration texture, porosimetry, optoelectronic and surface chemistry. We have dealing with different kinds of molecules and publishing in the last 10 years different molecules: toluene, phenol, 4-chlorophenol, rhodamine B, methylene blue, yellow 5, 2-propanol, toluene, and some others. And we know that we are able to control, by means of the absorption isotherms, the quantity of the total size of the absorption. For the case of methylene blue, that is the case I will show you because of the time. We are able to measure the surface density of the molecules absorbed in the equilibrium of absorbed. And when we take this number and multiply by the first order apparent rate constant, we are able to measure a novel kind of reaction rate that we call it global surface reaction rate. And this surface reaction rate, because it means with absorption, this is heterogeneous photocatalysis. So you need to introduce the quantity of absorption molecules within any kind of expression to measure in a proper way the reaction reactivity. I will show you some examples. Excuse me. You have to be mercy with me because I'm getting out of COVID. I was sick exactly three weeks ago, and still I have some problem in my throat, very dry, and I feel with some scars. It's a very strange sensation, but I'm still here. So, thanks to God. In the case of sulfur-doped materials, we are able to achieve an interesting linear relationship between the surface rate and the density of molecules absorbed. In this case, the photocatalytic TOF, PTOF, if you want to call it like this, is around 0.13 seconds minus 1. It means that they are in the range higher than nitrogen-doped carbons. I explain you later why. For the case of oxygen-containing or oxygen-doped carbon, we also achieve a very interesting relationship for different kinds of high surface area nanoporous materials. And we achieve an interesting point in this part of the surface density between the surface density and the surface of reaction. So then we deal a little bit with phosphorus-doped materials, and we were able to control the possibilities to form iron phosphide, iron pyrophosphide, or even iron phosphides. No, we are able to introduce the formation of phosphates, pyrophosphates, and phosphides. And we have already demonstrated that phosphides are not good for oxidation. That is what they expected, because in this case, carbon is very reduced and phosphorus is very reduced too. So these kind of materials will be very able for the reduction of molecules for the case of hydrogen photoproduction, but for the oxidation are not good. So we optimize the phosphate in this range of temperature, and using this, then we change the quantity of phosphorus, and we achieve a maximum of density, of molecular density for the absorption of methylene blue, and we achieve a very interesting relationship until the formation of pyrophosphates. Once the phosphides are formed, the reaction is decreased. So we need high oxidation state in the heteroatoms M-doped or sulfur-doped or phosphorus-doped carbon-based materials. In other words, we demonstrated, for example, that reduced sulfur oxidation state are able to control the selectivity of product, and instead of have sulfates, we use sulfoxides. We are able to control the formation of catechol from phenol. This is a recent work. And at the same time, we achieve a very interesting relationship between the surface density of molecules absorbed as a function of the pore confining effect, and in comparison, all the system in presence of sulfur shows a very high activity in the photodegradation of phenol. In summary, when we put all the data together for the case of methylene blue, we achieve a very interesting relationship with a good enough, it could be better, of course, but good enough quadratic linear factor of regression. But the important thing is the P-TOF for the case of methylene blue. By using different kinds of heteroatom doped carbon-based materials, we have values in the range of the industrial application. It demonstrates that this technology can be scaled up. Okay, so in addition, we know that we are not achieved the maximum for the methylene blue photodegradation. Why we know that? Because the reciprocus of the cross-sectional area of the methylene blue is around 0.29 molecules per nanometer quadrado. It could be over here. So this reaction is not in the maximum position. It means that we can achieve even better P-TOF in real industrial application for the degradation of this molecule. And the reason why sulfur-doped carbons are better than oxygen-doped carbon, and these two are much better than nitrogen-doped carbon, is because of the electron affinity. There is nothing new here. The electron affinity of nitrogen is by far very much higher in comparison of oxygen or sulfur. And that it means the higher is the electron affinity of the heteroatom, the lower is the P-TOF, because if we are dealing with excitation of electron and you have here nitrogen in your system, the electron does not go to the formation of superoxide anion radicals or hydroxy radicals. It would be captured by the atoms of nitrogen. So nitrogen is fantastic for reduction, but not for oxidation. There is nothing new here. Only there is a correlation of parameters. Okay, so all these photocatalysis and all these words are useful to solve the problem of the polluted water. The answer is yes. It's not only because in the practice, the CPC photoreactors are able to work even under critical operative conditions. This is a courtesy of my dear, real good friend, Sixto Malato. Thank you very much, Sixto. I am not sure if you are in the audience, but in any case, thank you very much for this picture. Reveals the possibilities of the solar photocatalysis. But we are dealing with a very important and dramatic problem all around the world. There is a lot of countries that are suffering an important and extremely reduced in the quality of water. We are talking about high water stress. In the case of Chile, we have been dealing by the UNESCO in the 18th position with the countries with the more possibilities to suffer extremely high water stress, and it was from 2019. And here is Kenya. I marked here Kenya. Kenya has very low photon flows in comparison of Chile. So if CPC photoreactors plays good enough in Kenya, more importantly, in very rural places, well, we think that it could be possible to put all around Chile different kinds of CPC materials. You can see in this infographic the dramatic situation of the reduction of the precipitation in Chile. Okay, in the desert, in the north, in Atacama, and so on, is even around 100%, or 100%, the reduction in in precipitation by rain. But even in close to Patagonia, in Punta Arenas, the reduction is around 40%. All the territory, we are suffering a lot with the reduction in the precipitation. So we don't need to be too much intelligent to say that we will have a very dramatic problem in the following years because it's not raining. It's not raining practically nothing in comparison of years ago, and it will have not only a problem of scared of water, but at the same time it will affect the food, the growth, and so on. So just only to finish, we have explored some possibility with this prototype, and we put someone in one school in the south of one of the regions of Chile. We donated this dispositive. That was the alpha prototype. That was the beta. The beta is more compacted and have everything. And the alpha, it was more exploratory, but it worked very well. We put it here in a container in the roof of the container of a school in a very rural place, and it works fantastically well. At the last, the children in this school has water with some important quality. So, just to summarize, I just want to say that bioderivative molecules and biomass wasted can be used for the sustainable production of free metal and free semiconductor carbon-based materials, and we are happy because I show you only the case of methylene blue, but this PTOF, this photocatalytic TOF, has been constructed by different molecules, and they are following more or less the same trends for the case of oxidation reaction. So I cannot finish without saying how thankful I am with my group. I have a very beautiful group that is part of my new group in the Universidad Autónoma of Chile, but also with my colleagues and very good friends. Po Xianping, associated researcher of the UDT and the University of Concepcion, and my friend and designer, industrial designer, Nesol Schbinden, Mazinger Zeta, Super Zeta, how I call him, because this guy is fantastic and skillful, and is a privilege to work with him. My two postdoctoral, Julio Urzúa in Daire Escudero, they work with electrochemistry and biological sensors. We are creating interesting appointments in the last month, and we are very focused for the following years. And of course, to my student, I will start first by the student of the University of Conce, Paula Muñoz, that the next week will do the defense of the PhD. She's dealing with the use of CPC photoreactors for the food industry dyes, and also dyes, very dramatic problem in Latin America. My other student from the University of Conce, Oscar Pinto, he's dealing with the production of nanoporous carbon-based materials for supercapacitors advices. And we have Daniela Quiñones, our new student of PhD in the program. I am the director in the University of Concepcion. Daniela is working with another kinds of functionalized biochar material for the remediation of soils, very important point in problem in Chile. And of course, I have to say thank you to my two beloved and little angels, Benjamin Luno and Antonia Castro, and they are my students of the initiation of scientific programs, and they are doing the undergraduate studies now. So it is important to say thank you to Luigi and Sixto for the kind invitation to this webinar, I am deeply sorry. I know that today I am a little bit slowly in comparison of my normal behavior, but I'm still a little bit sick. So deeply sorry for the troubles I can cause you. And of course, I have to say thank you to very good friends and colleagues from the CIPOA conference, Vitor Vilar, the president, Marcia De Sotti, Camila Morin, Renato Falcao, very good friend of mine. It's an honor to have your friendship and, of course, the possibilities to cooperate with you and some other colleagues from all around the world and the people who put the money from the Agencia Nacional de Investigación y Desarrollo. Thank you very much. I expect not to be spend too much time in this presentation. Thank you. I am open for the questions.
Excellent presentation and for inspiring us with your work. And now we have some questions for our audience. And to start, from YouTube, Amal El Sobati asked, what about hydrogen production using photocatalysts without using sacrificial agent? Photocatalysts that can achieve both hydrogen production and photodegradation simultaneously?
Oh, yes, of course. We can achieve hydrogen production and photodegradation. In addition, I can tell you, that we are able to produce hydrogen for even polluted water. That it is a reality. The group of Professor Sixto Malato have dealt with that. Okay, probably the yields of hydrogen production is not the best, of course, because when we are dealing with high purity electron donor molecules, the possibility for reactivity is much higher in comparison. But in my opinion, I think that we have a very, very polluted water that probably the cost of the remediation is too much high. Probably it could be better to sacrifice that very high polluted water to produce hydrogen. Yes, it's possible. But do not forget one important thing in the hydrogen technology. People don't have into account important features from the chemistry of the catalyst. When you have water and you try to get hydrogen and oxygen molecular at the same time, you require a bifunctional catalysis. People don't think about that. More of the works I have read in the bibliography don't take into account that they need a bifunctional catalysis, but because in that reaction there is two semi-reactions. There is a hydrogen formation and oxygen formation at the same time, and even the possibility to form other kinds of products as acetic acid and sometimes methane or formaldehyde, depending on the nature of the catalyst. But the direct answer, of course, is yes. We can do both processes. Some groups are dealing with that. Thank you for your question, Amal.
Now, Leandro Gurlat says, nice presentation, Professor Matos, and I hope you will be recovered soon. And ask, what would you be the method of choice for preparing titanium dioxide carbon photocatalysis by using commercial titanium dioxide and natural carbon source?
When we produce, and it's a very good question, Leandro, thank you. When we produce this high-bright photocatalyst, we are not dealing with commercial titanium dioxide. We start from the salts containing titanium, and at the same procedure, we introduce the doping of carbon and some other elements. Commonly, we have published different kinds of methodology, solvothermal or hydrothermal. At the same time, commonly, we are dealing with long periods of heating in conventional electric ovens, or even we have published the possibilities of microwave-assisted synthesis. We have published, for example, the synthesis of carbon quantum dots within the crystal structure of titanium dioxide and zinc oxide even, okay, by microwave-assisted. We have also published, for example, titanium doped within the micropore structure of silica. by different ways. We have published it by thermal synthesis, by using conventional autoclave reactors in thermal conditions, but also promoted by microwaves. So there are the two important possibilities. It's very tough to control quantum carbon quantum dots if you are use other kind of possibility. The reason is because the formation of titanium dioxide is an acid promoted reaction. It's a hydrolysis. If you are dealing with a starting point, for example, alkoxide, as isopropoxide or butoxide, for example, the hydrolysis is very fast. And if you have a very labeled proton, the gel is formed so fast that the size of the crystal are too high. So we are dealing most of time with very controlled pH of the condition of reaction. That is the trick of my group.
Thank you. Now we continue with question from YouTube. Getane Dires, I'm sorry if I'm not pronouncing the correct form, asked, can the intermediates remain absorbed in the pore of the carbon? If so, what sort of approach will be reasonable to use to avoid such absorption of intermediate?
This is a very good question. I know, Jetani. It is a pleasure, Jetani, to see you here. A fantastic and skillful doctor that has been studied with my very good colleague, Conchi Ania. A pleasure to see you, Jetani. Of course, there is a kind of competition. Depending on the dipolar moment of the intermediates, they can compete with the active site against the original pollutant. That's for sure. We reported in 2007 the influence of the formation. 2007, the influence of the formation of the intermediates in the degradation of phenol upon the photoactivity of titanium dioxide in accent and in presence of different kind of carbon. And depending on the polar moment of the intermediate, it is able to push out the phenol from the absorption side. And of course, this is heterogeneous catalysis. If you have a problem in the step of the absorption, reaction can go very well and readily deactivated. And the reason is because the accumulation of intermediate start to compete with the original pollutant for the active sites, for the absorption sites. So that is the reason why it's so important to do first the absorption isotherms, because the absorption isotherm told you exactly what is the initial concentration and the loading of your catalyst that you have to use for your degradation experiments. Because if you select a very high concentration with a very high surface coverage, what's going on? It's a crazy, because when you start to form intermediates, you can think about, in the case of a dye start to fragmentate, and from one molecule of dye, start to promote the formation of 3, 6, 9, 12 fragments from only one. And if they start to compete with the original pollutant for the active absorption sites, catalysis deactivated immediately. So it's very important. It's very important to know exactly what are the type of the intermediates, because they will affect, of course, the possibility of reactivity of the original molecules.
Okay. Now to continue, Catherine Gajardo asked interesting topic and consult, will participation certificate be delivered? And as soon as possible, we'll be sending you the certification, no worries. And the question is, how can this contribute to environmental protection? Thank you very much, and bless.
Well, I think that along my presentation. I have already answered your question, but no problem at all. It's a pleasure to say a few more words. It is evident that it is possible to establish a correct policy to help people living in the rural place. More importantly, people living in the rural place, because there's many places all around the world that commonly distribution water never arrive because there is no possibility of tubing. There's no tubing. There's no distribution tubing. So people take the water directly from rivers or squares or lakes or wells, for example. But each more and more, this water is polluted because even the a local agriculture management introduce some pollutants in the river. For example, you can have a very small house with 3 or 4 trees with tangerines, and you use atrazine to take off the plaques from your plants, and when then rains, that plague size arrive exactly to your own well, and then you took the well. Maybe if you're able to put this kind of solution in very rural places, you're able to trade your water. And I always say that it's more important to try to do something. It doesn't matter whatever you want to do, but you have to do something before do you use the water for the food. So you need to do something. And of course, this technology is able to contribute, and it has been able to. I am more than sure that you can use it, but it depends in what you want and the policy of each country. So.
Okay. I think the last question, Camilo Sanchez Tobon asked, thank you very much for the great presentation, Professor Matos, and how the carbon content?
It depends. Hola, Camilo. It is a great pleasure to say hello to one of my old students and very good friend. It's a pleasure to see you here, Camilo. I hope you are fine and your family. Thank you very much for your question. It depends. I have published it years ago that depending on the cross-sectional area of the molecules, you require different kinds of carbon content if you are dealing with hybrid photocatalysts. But if you are dealing with only carbon-based photocatalysts, the quantities are very few. The first problem of the CPC scaling up is that you require high quantity for semiconductor. And if you put loading in the ratio of 1 gram per liter, you can imagine the price of the pollution of water by CPC with classical titanium dioxide technology. It's not useful. That's not good enough to be efficiently and efficiently scaled up. But with carbons, the costs are very low, and the quantities you require of carbon are much more lower in comparison of titanium dioxide. The reason is because we are able to produce carbon with surface areas around 2,000, 2,400, 2,800. And very well controlled the surface chemistry. It means that if you have 2,000 meters square per gram in comparison of 50 meters square per gram of titanium dioxide, you can reduce dramatically the loading. When I'm dealing with carbon, only with carbon in absence of semiconductors, I am dealing with 0.005 gram per liter. So you can deal with a photoreactor of 15 or 100 liters, and maybe you use 1 gram of carbon. It's negligible. And the costs, of course, are very, very low in comparison of the cost of titanium dioxide. Thank you for your question. Camilo is a skillful chemical engineer, so he has to do questions in that way. Thank you, Camilo.
Camilo had other question and asked how the carbon affect the crystalline phase of the titanium dioxide regarding Anata's phase.
Commonly, you cannot affect it. The only matter you can change the crystalline phase of titanium dioxide if you are heating to temperatures around 1000 Celsius degrees. The change of anatase to rutilo start to appear around 800 in presence of carbon, but in a very high quantity of carbon. And at the same time, you have to introduce a reductive atmosphere. You require to put hydrogen in the flow, in the heating, and use a high quantity of carbon to introduce the change of crystallinity. It's not possible to change anatase to rutilo. On the other side, it is possible to control the formation of the crystalline depending on the biomass derived precursor. We have published it, for example, in several works, more than sure you have read it, that depending on the precursor furfural, chitosan, saccharose, the proportion of anatase to rutile change. For example, when you're dealing with saccharides, it's very, very interesting to form high quantities of rutile. And the reason is because the saccharides are able to be degraded at low temperature, and all that heating in the autoclave are able to be used for the change of the crystalline phase. That we have found, but that is not that is not commonly to find it. Normally, you achieve by solvothermal or hydrothermal way, you achieve the most important, that is anatase.
Now, from YouTube, Andrea Oyarzun said, thank you for the talk. And she's curious about the final end of the pollutant in the water. Are they filtered then or transferred into less harmful species?
You are not filtered, Andrea. Thank you very much for your question. Andrea is also a very old student from our University of Concepcion. It's a pleasure to see you here, Andrea. Hope you're fine. You are not filtering nothing at all. From the beginning, you have a continuous flow system, and you are going from the tank to the tube of the reactors, and you are dealing again to the tank, and so on. And you take some aliquots time from time, and you do the analysis. In the moment you have achieved that the total organic carbon is almost to zero, you know that all the pollutants and the intermediates have been already degraded, and you have water in the most high purity quality. Okay, but the only thing you need to filter after you have already depolluted all the pollutants and the intermediate is the catalyst. And in this case, also it's much better to work with carbon than with titanium dioxide, because it's easier to filter carbon than titanium dioxide. Well, depending on the size of the carbon. If you are dealing with graphene and it is very well dispersed, you need a very, very interesting filtration system. But it's not the case. Commonly, we introduce nanoporous carbons in the size of 18 to 100 micrometers micrometers in particle size in average. So it's very easy to filter that kind of material. So you start with a pollutant, and this pollutant, during the degradation, the final products are the mineral ones. This technology is also called photomineralization, because all the organic products are converted in mineral products. For instance, if you have phenol, you will have for one mole of phenol, you will have 6 moles of CO2, and the rest is water. Okay? But if you have, for example, an azodide with nitrogen or sulfur, in addition to carbon dioxide and water, you will have mineral acids. But mineral acid, there's not a problem because you can filter with a filter of carbon. So that is an important, another important advantage of using carbons. It is interesting when you do theoretical estimation of the change of pH expected for the formation of nitric acid or sulfuric acid, for example, when you are starting from yellow 5 or you are starting from atrazine, different kinds of azo-dyes, you can estimate that quantity of nitric acid should be formed, and it should be half, and they will promote a reduction in the pH of the solution. And theoretically, you expect a reduction in the pH of solution, but in the practice, they are not decreasing as much as the theoretical estimation predicts. And the reason is because an important part 70-80% of all the inorganic acid are absorbed on the own activated carbon. Activated carbons are very well known, probably the much better absorption filters for mineral acids.
Okay, I think with this last question, we can conclude with this webinar. Thank you very much to everyone for participating in this important instant, and thank you, Professor Matos, for your excellent presentation. It's important to remember and that we care about your opinion. By channel YouTube of channel and by Facebook, you can find a short survey to know how we can improve, or if you need a certificate of attendance for this webinar. See you in the next opportunity. Have a nice day, Professor.
Thank you very much, Daira, and of course, thank you very much all the attendants. It has been a pleasure to give this webinar. I am deeply sorry because I'm still a little bit tired of my throat, but next time you will see me with more energy than you expected. Okay, so thank you very much for the attention, and I hope you are so good, and see you in the following months in different conferences.
Bye-bye.
Ciao.